So we have seen the detectable precedence filtering rule. We have seen the overload checker. The last one that we will see is the not last rule. The situation is the following. We have 3 activities there, and we see that it's impossible to have C that is scheduled the last one in the set of 3 activities. So C cannot be placed after A and B. The best case for placing C after A and B is this one. We have A, then B, and then we try to place C at the end. And we see that's impossible because we are beyond the deadline of the activity C. Therefore, C must end before A or B, or possibly both, right? But the best case, so the one that is not removing any solution, is this one. We will take the maximum between the ends here, between the two values there, and we will use that value to update C. Okay, so that value corresponds to B would be placed after C. Okay, in that case, okay, B would be placed after C. That value would correspond to A is placed after C. Okay, we take the maximum of the two situations because we surely do not want to remove any feasible solution, and therefore we will update the deadline of C, the latest completion time of C, to that date, right? That's the not last rule. We detect that C cannot be placed the last one, and therefore A or B should come after, and we will take the best of the two situations from the point of view of C, because we don't want to remove a value that would still be part of a solution for the activity C. So let's write down formally this rule. So we have that the earliest start time plus the processing time of a set omega, if it is larger than the latest completion time minus the processing time of the activity I, then we can safely update the latest completion time of the activity I, and we will take the maximum over all the activities there in the set omega. Okay, so that's the not last rule because we detect that the activity I cannot be placed the last one. It cannot be placed the last one in the set omega union I. I cannot be placed the last one. So in our example there, that would correspond to the set omega, and the activity C would be the activity I, and I cannot be placed after the set omega. Okay, the problem is that we need to enumerate possibly all the set omega, right? All the subset omega of T, and we do not want to enumerate them all. So let's be a little bit pragmatic, and we can first observe that if we would have one subset omega for which the rule would actually filter the latest completion time of I, it must be that it forbid for a set omega that belongs to this set, the not last set. And this set is exactly the one. It's composed of the activity J, so that the latest completion time minus the processing time of activity J is less than the latest completion time of I. So that's exactly the set for which, when you take the minimum between these two, okay, you can drop the minimum there, and this one, okay, the maximum there, okay, will be less than the latest completion time of I. So if we have again a subset of omega, so that we have an update of the latest completion time of I, it must be a subset here in the set of that we call the not last set of the activity I. So let's study on this small example which activity would be part of that set from the point of view of activity I there. Okay, so clearly this one will belong to the set because we see that there, okay, the latest completion time minus the processing time is less than this. Okay, this value there correspond. So if you take this, that's the latest completion time of I, right? And that's here, this one, that's the latest completion time minus the processing time. So that's the case. So it means that C must be part of the not last set of the activity I. For the same reason, that one will also belong to the not last set of the activity I, but this one will not, because you see that this time value there falls after the latest completion time of I, and so if it would be part of the set omega, we wouldn't have any filtering on the latest completion time of the activity I. Okay, so that's why the activity A does not belong to the not last set of the activity I. So that's the not last rule. We have made the observation that if we would have some filtering, it should be in a set omega that belongs to the not last set. But the question then is, does there exist a subset omega that belongs to the not last set that triggers the first part there of the rule? Because if we cannot have this true, then we cannot trigger the filtering. So first we need to check that there is a subset omega that have this first part of the rule that is true. What we can do is take the maximum there over all subset omega prime of the earliest start time of omega prime plus the processing time of omega prime. Because if for the maximum of over all the subset omega prime in the not last set, if it is the case, okay, if it's not the case for the maximum, that it's not the case for none of them, okay? So it's a mandatory condition that for the maximum of the subset omega prime, this is true. If we want to have a chance to filter, this must be true for the maximum. Okay. So clearly, if you remember the definition of the earliest completion time, this corresponds to the computation of the earliest completion time of the set omega prime. So, sorry, this corresponds to the earliest completion time of the not last set of I. Okay? Taking the maximum over all of them, all the earliest start time omega prime plus the processing time corresponds to the definition of the earliest completion time. So you can already imagine that we will use theta-threes for that, because theta-threes are very useful to compute the earliest completion times efficiently. So let us make this rule a little bit more efficient. So the existence of a subset omega that belongs to the not last set that would trigger the rules can be tested using this. Okay, the earliest completion time of the not last set of I. The problem is that once we have detected this, we still don't have a subset omega that we can use for the second part, which is the update of the latest completion time of the activity I. But do we really need this set omega? Not really, if we accept to relax the filtering, okay? Because the filtering is this one, right? That's the filtering. Sorry. The filtering is this one. That's the filtering that normally we should have, right? In the wood. But if we take a proper set, if we take a set that include this set omega, and that will be the case with the not last set, then we will have a weaker filtering, but that's also acceptable. As long as the filtering is valid, that's acceptable. And so this is what we will do. We will take the maximum of the latest completion time of J minus the processing time of J for all the activities in the not last set, okay? And so we don't really bother about taking the maximum for the omega. Okay, we will simply take the whole set so that we possibly have a weaker filtering, but still it's a valid one. So that was the original not last rule, and our weaker filtering rule will be that one. Okay, so first we will check if the earliest completion time of the not last set is larger than the latest completion time of our activity I that we want to prune. And instead of taking the maximum here of the latest completion time minus the processing time over the set omega that has triggered the rule, we will say that we do not really care about which set omega was the one that triggered the rule. Okay, we know that the earliest completion time is larger than this. That's fine. And we will simply compute it because it's a maximum. We will compute it over the whole not last set, which means that the not last set might be a set that includes the omega. So that's why the filtering is a little bit weaker, but that's easy to compute, right? Because here we have a very efficient way to detect if the rule applies. Okay, if we can apply the filtering, and then we don't care about which omega was the one that triggered the filtering. We will compute the maximum over the whole not last set there. That's not last prime. Again, the filtering is a little bit weaker, but the fixed point will be the same. So in order to implement this efficiently, you know that we need to have nested sets. Nested sets is really key if we want to apply the incremental computation for the earliest completion time of sets. So the problem is that the not last set, you see that it excludes the activity I itself. Okay, and that's why it's a little bit a problem to have nested sets. So we define the not last set prime. That's exactly the same definition, except that we forget about excluding the activity I. So the activity I can be part of the not last set of I. Okay? And because of that, we will have nested relations between the not last set prime sets. Okay? But in what order should we consider activities to have nested sets for the not last set prime? That's exactly this order, right? So we will consider increasing not latest completion times. And so if this is the first activity I, the first one that belongs to the not last set of I is A. Then if you move to the second one, okay, you have the 3 there, and that will be the not last set, okay, of the activity 2. Then if we move one more there, you see that D will also be part of the not last set prime of the activity 3, and so on and so forth. So that's the order in which we should consider the activities so that we have nested sets for the not last sets. Okay, so if you sort the activities according to the latest completion times, then you have nested relations for the not last sets of the activities. Okay, so that's clearly the order that we will consider to compute the earliest completion times using a theta-tree in the filtering algorithm for the not last implementation. So we sort the activities according to the latest completion time, as I said, and we will also sort them according to the latest completion time minus the processing time. Okay, that's exactly because of that order. You see that in that order they will be added one by one, so that's also an important sorting. So we have two important sorting there, this one and this one, and this is what we do in the algorithm there. So in the algorithm we sort them according to the latest completion time and according to the latest completion time minus their processing time. Okay, we initialize the theta-tree. Initially the theta-tree is empty, so we have no activity in it, and eventually, so for each activity I, what we will try to do is that the theta-tree will be equal to the not last set. Okay, it will contain the not last set of the activity I. This is what we will do there in the while loop. So in the while loop, what we do is that we will add all the activities so that after the execution of the while loop, so there, this is true. So that will be what we will have as a property, is that the theta-tree will contain the not last set of the activity I. Okay, and we can add them one by one because here we will consider an iterator there. That's an iterator that will iterate according to the latest start time order. Okay, the latest start time order, so according to this order. And this is why we will be able to add them one by one. Okay. Once it's done, we check that for the not last rule, the premise is true, that we can trigger the filtering. And so we need to verify that the activity I cannot be placed, the last one, in the not last set. And this is what we do. Of course, because we use, the not last set prime, we must also remove the activity I from the earliest completion time. Okay, so we remove the activity I itself. And if we exceed the latest completion time of I minus the processing time of I, we can compute the new latest completion time for the activity I. Okay, and it will be the minimum between the previous one and the new one. And that is true because here, the activity J that we consider that we have there correspond exactly to the maximum over all the ones in the not last sets because they have been ordered. Okay. what we will have is that J is the one that will induce the least filtering for the update of the latest completion time of I. And eventually, we update according to all the updated values that we have computed, right? We update them for all the activities I. So let's see what's the time complexity for this algorithm. First, we have the two sort there. That's clearly n log n. Then we have the initialization of the theta-tree. That's also n log n. Sorry. So that's n log n. Then we have this loop. And this loop will consider each activity one at a time. And exactly each activity will be inserted at most once in the theta-tree. So considering each activity and inserting them in the theta-tree, that's also n log n, because each insertion takes log n. Since we will do it at most n times, that's n log n. And this update, you can do that in constant time. So overall, this algorithm also executes in n log n. So that's very efficient, and it will be able to update all the latest completion time of the activity in n log n. In the next video, we will see an example of execution of that algorithm.